an application, then followed by any questions you get on the live show. That's the agenda for today's session. So first we'll go to the assignment show. So we were actually interested about solving problems on linear list applications. So just to give you an idea, so where are we moving here? We started with the first topic here, ad hoc thinking, and how to solve problems here, varieties of problems, on the fly thinking, and merit of the problem, which may not be called as a pattern ideally speaking, but each new thought you are getting for a problem, we give some label like ad hoc thinking here. Then later we discussed one classic pattern called binary search thinking pattern. What kind of problems now, what kind of search is normally here, that kind of binary search pattern makes sensible. Then later, so we have finished up assignment on divide/purne also. We have given the thinking process and what kind of problems again here divide/purne thinking makes sensible. So they are mostly useful to get logarithmic algorithms and everything. That's what we have discussed till now. Today's session is slightly different. So we got a data structure which is a linear list. So and a bunch of elements with relative relationship. That's all we mean by linear list. One of this linear list is available as a end user point of view. For what kind of problems now this linear list is useful in practice now. We have seen that as a data structure and implementations in our videos now, but from a problem solving point of view, which kind of context now linear list makes sensible. That's the whole point of this assignment. Let's pick up the first problem here. Single linked list implementation. In the class or video, we have discussed the implementation of list using single linked storage. Implement the same here. There's nothing much to discuss in this problem, but to just give you an idea what we are really trying out here. So there is an API, we have given it up for linear list. For short name, we always give list. List API is available as a black box. Now assume here, these are all a bunch of elements now here. So with relative relationship, now you can insert wherever you want, you can delete, you can insert, you can delete, you can traverse here in whatever way you want it up. This kind of operations mostly make sensible on what they call list data structure. From data structure point of view in the real world, wherever such kind of collection is available, we map to this logical name. But just name is not enough. Operations make sensible. All these operations are index driven. What position you want to insert, end, start, or wherever, remove, replace, all index driven and everything. But how to get this behavior from implementation point of view? So from APIs, black box given to you, how to get the implementation? Different ideas we have discussed. The first one is a sequential, and the other one here is linked storage. There are two more storages are also available, which are called hash and tree storages now. So all these are a fundamental storage techniques available for any logical data structure while implementation. Sequential, we have done it up. We call it as array list now, or sequential list, or some language they call it as vector. And I've seen the complexities in the video. But linked in the videos I have discussed up double linked implementation, because that's the most practical implementation. We see it up because a lot of flexibility is available. So you can traverse either way with a double linked list. If any node pointer is given, you can delete it up, you can insert before. A lot of advantage in practice here because of double linked storage. But just for practice purpose, I'm asking here, so implement this by using single linked also here. That means each element now so you got to store in this fashion. So this data, whatever is there in physical level, keep the data here. Only one single link is allowed in a wish. Second element here, again, in node we are creating up, data is here, this is a link. This is a link here. If you don't have link in a way here, then we do not know what is the next element relative order. That's why the link whole point here is, I want to maintain the relative order. This is what we are using up. In a doubly linked storage, one more link also available, which points to this previous node. So that's what ideally the difference here. Now the next element again here. And if you want, you can keep a dummy node too. So that's what ideally, logically, we show in this fashion. Last node, nothing. Here is some data, here is some data. Now if asked to do insert element here, ideally, so you have to implement this in single linked list. So let's say if index 1, this is index 0, index 1, you have to insert an element. So do some kind of work, required work to get all the operations which you have done it up in the sessions, in the video session. That's what the first problem. and analyze the complexities now here and compare with double linked storage here. You try to really see it up, is there any difference or not here. Some specialized operations which we didn't implement in the class also. Maybe a classic example here is I give a node, remove this node from a list. So I know the index now, remove the node. In a single linked list now, if you want to remove this, how are you going to remove it up? Because I cannot move back to really unlink this way here, and you must traverse it up, which really takes a lot of complexity here. But double linked storage now, we can go back, we can able to unlink it up. Those operations when include it up, so just look at in the video, mostly I didn't give up this kind of an operations, given a point, remove that node. But if such kind of operations required, double linked makes more sensible. That's why. So single linked just for practice purpose, I'm asking out here, do that as part of this assignment question. It gives some kind of understanding about pointer manipulations and list linked implementations too. So that's what the first problem in detail show. Second problem is a little tricky. We're asked to implement double linked list but with single pointer field. So let me write this. This is first problem here. Let me talk about second problem here, which is double linked list using single pointer field. So the first question we always get it up is, when I said double linked now we want to traverse back. That's why we are keeping second pointer. But the question asking is a little strange. With a single pointer field, how can you get that? If you recall an example here, let's say the first node 10 is available. Now we'll keep that previous link. This is a traditional double linked list. There is a 22nd element in the list. So third element in the list here, just an example I'm giving out here. Let's say 15, fourth element here, 4 elements are available. So the address of this, we assume this as 1000 here. There is a node, there is a data, there is a pointers now here. There's a lot of things, the terminology wise, you got to be careful while doing these implementations. So this is data part. Ideally in some languages, if it's a primitive, it's okay, but if it's not primitive, even this is also pointer innovation. That's why. So this just for understanding purpose, I'm writing 10, 20 as a primitive values. Languages may not give you primitive sometimes here to keep as part of some, like Python language now, everything is a pointer. Such case, you should refer them like a pointer. But just for understanding purpose, I'll keep as part of the node itself now. But this is a pointer now, pointer to this node. This is also a pointer, and some language like Java, they call reference pointer to its previous node. Whole of this together structure is called node. The whole point of node here is there is a data, there is a next, there is a previous, all of them together we call it as what they call a node. This is second node, third node, fourth node. Now, so the address 1000 means now the starting address of the node here. That means this first byte of this whole node structure. That's what we mean by 1000 address. Let me write second node address, some dummy address now. A 2000 assume here. This is 3000 here. This is 4000 here. Just an example. So ideally, what you're storing out here is 2000 directly we are holding it up. So, but in reality, we just show an arrow. But in practice, there's no arrow concept. Just numbers are stored up. Addresses like other numbers. Here we store the address of the previous node, which is 1000 anyway. For understanding purpose, we show an arrow like this. But ideally speaking, there's a 1000 number over here. Next, so one more pointer here. Again, one more pointer. One more pointer here. One more. If it's a circular thing, which we discussed in the class anyway, that's more practical thing. Benefits are given. Just for understanding purpose, I'm just keeping up a linear thing. Just a null. There's a null because null means on some special value we store it up. And you can have a pointer to this, so to traverse these elements of what they call list. So this is a traditional double linked list. So now if you want to move forward anyway, we just go to this node, this pointer will take it up, move next. Go to this node, access this path or access this field, I can call it up, go to the next node. Go to the next node, again access it up, go to this. That's what ideally we are doing. Reverse exactly same thing here. With 2 pointers we are able to manage it up, but I'm asking here to get similar kind of effect now with only single pointer field. That means my requirement is simply now, I just write it up here. So now only one node, one pointer field I am allowing. So now take second node here. I'll take third node also. There is a fourth node. Now only one pointer field I am giving up. Data is still same, 10, 20, 30, 15. Now if I store only next guy anyway, so if I store only this address, maybe 2000 if I keep it up, now you can only move forward. But from here if you want to come back, how do you come back? Because 20 consists of 30 node address now, 15 node address. But that's not the right implementation. You must get both traversals now, but a single pointer. That's what the tricky part of this question here. Now, what should I do now? So we cannot store just one node address now here, a previous or next. That's not going to work. You got to do something else. That's where again we are going to utilize a tricky thing called exclusive OR. You have seen in the ad hoc thinking here, exclusive OR one of the benefits now. Similarly here we are going to see up exclusive OR benefit. So what do you mean by an exclusive OR? With whom we are going to exclusive OR operations? So this is what the operation we call it as exclusive OR. If I really give up a 10 for example here, exclusive OR, this is symbol we use it up in our programming, a bitwise operator, so it becomes 0. Any number when exclusive OR with itself is 0, and if I exclusive OR with 0, we get always same number. But in what sense this is going to be useful? First let's look at the context, then I come back, we'll see in what way exclusive OR is getting useful. Now here, previously we stored what they call next node address now. Now here, next node address is 2000 here, but here I don't want to keep 2000. Look at previous node also. For first node, there is no previous node now. Assume here 0. 0 and next node, exclusive OR, both of them is stored it up. That means 0, exclusive OR. The value I'm storing here is 2000. Just number, we are keeping it up. That's all ideally speaking in this path, one single field. Here what do you do? Take the previous node, take the next node, take exclusive OR of that. 1000 is this node address, 3000 is the next guy, take exclusive OR of that. That means here we keep up 1000 exclusive OR, 3000 inhibition. That's what we are keeping up. 30, 2000 is this node address, 4000 is this node address now. Take exclusive OR of that. 2000 exclusive OR, 4000. Finally, 3000 here, exclusive OR 0. So because for 15th node, next is not there, we are taking that as a 0. Now if I store this kind of value, while creation of the list now, let's see, are you able to get this double linked list behavior, both traversals behavior or not? Now we are starting from here. Now assume I want to move forward, what do I do? So I'm here, so first node is 0, I'm assuming here. To move forward anyway, take this address, take exclusive OR with the previous value. This value 2000 exclusive OR 0 is same thing now. Again I'm asking exclusive OR with the previous guy. What do you get? Nothing. Same thing here, 2000 on. Means this node we are going up. But from here, you want to go to next node. So from here if you want to go to next node here, take this 1000, 3000 value. And since we are coming from this node, this address already we know, since we are doing left side traversal, that address whatever is available, exclusive OR over here. That means at this node, that means here, what we are asking here is take the existing value, 3000. Now you exclusive OR with what now? Since left to right anyway, take left side node address, do exclusive OR. Left side address is going to be 1000. If I do that, A exclusive OR, B exclusive OR, say I'm doing here, it's which order you want to do this operation. Exclusive OR, order doesn't matter here. This operator is associative here. That means if I give A exclusive OR, B exclusive OR, C is equivalent to, you can take A exclusive OR B, then exclusive OR C, which is also same as A exclusive OR B exclusive OR C, like this. So the order will not really impact the exclusive OR. Take some examples, you can get a clarity on it. That means whichever order you do it up, output is same. So by using that, since I'm asking these two here, so let me take these two first, then with 3000. 1000 exclusive OR 1000, it becomes 0 now. 0 exclusive OR that is 3000. So at this node, of doing what they call this exclusive OR operation with the previous node, I'm getting next node address, which is 3000. I'm able to move next. Again from here, if you want to go to next node here, what do you do here? Again at this node, the value we have here is 2000, exclusive OR 4000, and exclusive OR with the previous node here. This node address is 2000 here. Now again exclusive OR, this x exclusive x will cancel out 0. 0 exclusive OR 4000 is 4000. That's why we are going to next node. Again here, if you want to go here, 3000, 0, and again 3000, so 0 comes up, means obviously last node, you stop there. That's how you can finish up left to right traversal. If you want to finish right, do the right to left traversal, exactly same. While coming up in this direction, take this node address. Since are coming from right here, so the next node address, whatever is there, if exclusive are, you can get a previous. An example here. So I'm here, I want to reach this node. So whatever the value, you take it up. Exclusive are with 4000 and away. 4000 cancels out, 2000 will remain, we are here. Again from here, if you want to get to the previous node, so this is a value, next node is 3000, exclusive of that will cancel out, 1000 means first node. Again here, 2000 cancel out, 0 means first node, you stop the algorithm here. Ideally means what? The single pointer field, it's very much possible here to maintain what they call, to get this kind of left to right, right to left traversal, like a regular double linked list, you are getting it up. The only thing here is, instead of just storing up next or previous value, which can only give one side traversal, but if you store exclusive or of previous node and next node in this pointer field, it is possible to get it up. That means one link per each node, we can save it out here. That's a benefit if you really look at the meaning of the problem here. But there are some issues with this kind of thing. For only traversal purpose, this makes sensible. But suddenly if I give this node address here, ask to remove that node, such kind of things are not going to work. Only thing we can able to get with this kind of tricky implementation was start from here, keep on going to the end here, start from the end, you can just do iteration. For iteration point of view, this kind of implementation is very classic. But if you want all tricky operations like a middle, go do something, and again pointer is given, remove that node, all these things cannot be possible here, the way we have stored these values. That's why the advantage is pointer field are saving it up. The benefit is both traversals are possible, but negative aspect here is general API is not going to possible on this kind of an implementation. That's what the pros and cons of this kind of idea. But all of this is based on a simple exclusive OR operation. Because of this specialized property, the way it is behaving and also associative here, we can able to get this behavior here. That's what we really mean here, this second problem, how we can able to actually solve it. If you want to really try some kind of coding, try this coding here, but this interview, this kind of question, they ask you to test the skills of what they call, how this single pointer we are able to manage it up here. That's the second question. So third question is last man standing here. A king gathers all the men in the kingdom who are to be put to death for their crimes, but because of his mercy, he will pardon one. He gathers the men into a circle and gives the sword to one man. The man kills the man to his left and gives the sword to the man to the dead man's left. The last man alive is pardoned. So there is a kind of process this king is following it up to give mercy for one single guy. So they're asking here, what is that single guy? Maybe in this case I'm asking last two people. Ideally, so we need that last guy. So who is that person got mercy by following this kind of idea, what this king is following it up here. Let's take some example to understand what is the requirement, last man standing here. So let me write problem 3 here. We call it as last man standing here. Just take off this exclusive OR part. Now let's take some n equal to 5 people. What is the process the king is really following up? Let's understand it up. So they are in circle now here. I'm giving up. Let's take a little more here. N equal to 7. So 1, 2, 3. So 4, 5, 6 here, 7 here. Now each person is standing here. So second person, third person, fourth person here, fifth person, sixth guy, and also seventh guy. Now, so we start from here. That's what they're asking here. Start from which person here? The man kills the man to his left. He gathers the men in circle, gives a sword to one man here. So which man? They're not really giving up. We assume that we start from the first guy. So we are here. So this guy we are really giving up the first sword. So what is doing out here? So the man kills the man to his left and gives the sword to the man to the dead man's left enemy. So if a man is standing over here, right, left is this guy anyway. That's why he kills this man anyway. Whoever is left of this guy, he passes sword anyway. Means first step, now the sword is here. Now, so we kill this guy, now pass the sword over here. Now here this person is now in control. Now kills this fourth guy, passes to this guy here, the left of this dead man here. Again this guy, what do this guy do now? Kills this guy here, passes to the left guy here. We are here. Again, so what does this guy do here? He'll kill the next guy here, left here, and passes to the left person, whoever is remaining here. Now, so here is a sword. Now here, again this person kills this guy here, passes sword to here. Again, what does this guy do here? So this guy kills this person here. Now, so is now exactly the final person, 7. If you want 2 people, 3 and 7 are remaining here. 7 is the remaining person. So all we are asking here is, this guy is survived here. Now return that number. The problem is simple. You give n value here. There is some process there, given in this problem statement. You got to, by end of this guy, which person is standing up, return that number. Input is the total number of people. Output is the survived guy. If you want 2 people, return 2. If you want only 1, return that 1. There's a slight variation is all, the problem is demanding. But how do you get this? How do you model this in software? So in real world, it looks like some generic puzzle, some kind of, arbitrary puzzle. But in software, if you want to do that, now we don't have to look at a little more mathematical aspect of that. Is there any math equation can I able to build to find this number? It's possible, but this problem, I'm not demanding that. I'm asking a linked list application only. Later, when I take math topics now, I'll ask you to build up some kind of math intuition to map up the survived over here. It's possible, we don't know. But later we talk about it. But here, how do you really simulate this process of circular natures now? The problem is always linear list. It's like a left to right, there's end point is available. But circular list here, there is no end point in here. So we didn't discuss the circular list in depth in here, but a slight variation you can able to implement circular list also. In a practical world, this kind of requirements are mapped to some kind of data structure software, which is circular list. Like a linear list, this could be called a circular list also. How to implement circular list? You have your choices. You can implement sequential way, you can implement linked way. Hash tree will not make sensible, we know. But these two we can use up as far as internal implementation. But from data structure point of view, from model for the real world data, this is what you call circular list. That's what we have it up here. Now the question here is, what do you do? Which kind of model, implementation makes sensible? Since I want circular list first here, you can create a node for each of that, and or you can use array also. If you use array, if I want to remove something here, then array if you want to remove some element in middle or some arbitrary index, shifting all elements is a painful. That's why the circular list data structure, what we have in the real world, now for this process, you try to implement with the linked storage. Linked storage, we can able to take off easily by unlinking at any point in a way. That's why. So this circular list, we always implement by using something called linked innovation. That's why circular, what they call linked list. Circular sequential list is also possible, but pain here is going to be the movement of elements now. Circular linked list is a proper implementation thing here, which makes sensible. So what do I do now? Simply create a linked list here. The last node will be pointing to the first node, because that's what logical mapping here. Now exactly replicate up, start from here. Now, so immediately what they call, kill this person out, means remove this node from a linked list now here, then pass to the next guy. If you remove it up, he is the next guy anyway. After removing this node, we are here, move left. Again, what does this guy do? Remove the next element in a vision. Again, go to the next element. Remove the next element here, go to the next guy. Again, whatever element available now, next remove the next guy, move on to the next. Finally, when single element is there, stop the algorithm. It's like a very simple straightforward API call. If circular list is already available, just delete next here, move next, delete next, move next. Repeat this process until the guy which points to himself here. That's why that node whatever is available, return it out. So this is how some of the real world processes, when you really cannot find up any mathematical approach, at least you can simulate it up. So by using a circular list now, we can simulate this process, get the result. That's what ideally we want it up. We're not asking for any efficiency in the algorithm here. Here only I want to show you linked list how can use for simulation purpose. That's what the problem number 3, which is last man standing in a vision. Very close to that is 5th problem. Then we come back to the 4th. The 5th problem is called repeated Josephus now. Here, so the only difference they're asking out here is the counting out begins at some point in circle, proceeds around circle in the fixed direction. In each step, a certain number of people are skipped here and the next person is executed up. Now slightly different process is given here. Let me take an example here to show you this process. Mind you, your language may not give you circular list out of box if it's not available. Now we have seen how to implement your own linked list now. Now just point next node to first node here. Keep following up circular linked list implementation. The class have given almost all the linked lists circular in nature here. So you take that as an advantage now. You can have your own thing if language doesn't give you. But real world needs are this. If your language may give or may not give, it's not our botheration. If library is out of box available, go and use it. If not, implement your own. That's always you have to think of it. You cannot say I cannot do in Java. So because library is not giving up, the whole purpose of this course is even if you want your own data structures, you should design from scratch at least basic data structures. More complex data structures, we see in advanced course how to build up anything in the world, even which is very, very high in requirements to model reality. But now the repeated Josephus, write this fifth problem here. We call that as repeated Josephus. So again, I'll take a bunch of people here. This time 1, 2, 3, 4, 5, 6, 7. 7 people I'm taking up. K is expected up. That's what the argument here. How many people to skip? If K equal to 2 now, K minus 1 person are skipped. Kth person is killed in circle innovation. I'll take K equal to, for example, 3. Here, first you are killing the person, then we are passing that. But here, first you have to skip it up, then you have to kill the kth person. If I give K equal to 3, every third person we have to kill it out. 2 people you have to skip it up, then you have to kill the third person. K minus 1 we are skipping up. Let's start from here again. So 2 people you skip it out here, third person again. 2 people we skip it out here, third person is killed up. Again 2 people we skip it out here, third person is killed up. Again 2 people we skip it out here, third person is killed, sorry. Now 2 people we skip it up, then again third person is killed out. Again 2 people we skip it out here, third person is killed. Final survivor is going to be 5. So you got written that. Again, we are not asking any mathematical expressions for this. All I am asking here is how to simulate that. Again, the actual mapping is circular linked list now here, but slightly different now. First you move K minus 1 times, K minus 1, movements you have to do with iterator here. After that, kth node wherever you are here, just take it off. Again, K minus 1 movements now, kth guy node you remove it up here. While implementing here, should I use a double linked or single linked now? Now you definitely get some kind of clarity. If node is given, if you want to remove it up, go to double linked and every here, otherwise keep single linked here. So I recommend to double linked here because that's practically always we are going to use it up here. So circular, a double linked list is all you got required for both these problems. Complexity, you're not interested in this problem. I didn't ask also here. All I'm asking here is written the result and also the simulation process. The linked list practicality, how to use it, practical requirements now is the essence of this assignment here. So that's all about fifth guy. Now what is fourth problem here? So this is broken keyword. So let's look at the problem statement of the broken keyword. You're typing a long text with broken keyboard. Well, it's not so badly broken. The only problem with the keyboard is that sometimes the home key or the end key gets automatically pressed. Means you are typing it up, suddenly some kind of issue with the keyboard. These are automatically pressed internally. But what should I do now? So when home is available while typing, so suddenly your control goes to home, start up the typing what you're typing up in the line. When the end key is pressed up, it is taking up to the last part of the string. All you're asking here is, after doing such kind of some typing on this kind of automatic pressing of home and end key, what is the final text you are going to get it up? They give some examples now. The 2 strings are given. We'll take one string now to understand the problem statement here. So they gave this guy here. This underscore is underscore a underscore. This is a home key they're asking out. BEIJU underscore text. So now this is all given to you as input now. Like this, the multiple strings now, let's do it for one string now, each other string now, you repeat the same logic here. Now, So this is input now. That means your problem you can think like input is string now with home key and end key are pressed up, and also other characters normally. Now what is the final text? You are going to get it up by executing this end and home whenever they really pressed automatically. For this example, first character T, this is not a special character, we copy here. H is alright, I is alright, S is alright, underscore, I is underscore, A underscore. But when the home key is pressed up in the input now, when the specific character is home, you just have to go to start now. Now my control should go to this place. So once your control goes to here, what are you doing now? B, I, J, U, N, A, V. That means, so this guy is replaced by B, this guy is replaced by E, I is now replaced by I, J is here. Now, U is also available, U is available now. After that, end key is available. So end key means from here directly jump to the last character now. So that means this point and so this point again, what is available here? Underscore now here. So there is a underscore again available here. So underscore. Then text now here. T-E-X-T. This is our output here. So finally, so the input is string now. The Bijou text now is what this guy expects as an outcome here. This is an output. This is input here. This is output. So all you have to do now is input is a string, output is also string now. But what logic are going to write now to get from this to this? So that's what the essence of this problem. How I'm going to really get this kind of Bijou text when input is given like this. Again, problem is very simple. All you got to do here is, so when these characters are coming, you got to pick some data structure. So where you keep these characters one by one. You keep on checking some kind of data structure. I need it up. Relative order is very important here. The order of the characters are very important. So list or array are the two possible candidates now. But should I use array or should I use a list now? If you ask it out, if I use array, I need a fixed size, but we do not know what is the output size now. When so many end are available, characters are available, what text size you are going to get when unsure of it now? Array we cannot do that. That's why better we take a list now. Whenever a character is a valid character, insert into the list now one by one. When home is coming up, move directly to the start of the list now. So that's where go to the start of the list now, very much possible. Then again the remaining characters, keep replacing the elements now in the list now. Then when n character comes here, move to the end of the list now here. Then again start adding one after the other. Adding at the end, a replacing element here, and also moving to start end. All these are very much easier to manage on a list data structure, because the API is really giving all of them out of box now. So take a list data structure internally. So manage these operations now based on the character now. The final output whatever comes now, convert into string, return that string here. That's all we read it up. So one scan through that is more than enough here. But where you want to move it up, start end here, list API. If you available, use it. Otherwise, you can write a simple operations too. That's why just a straight example of how list can be used up as a black box now while solving the problem. That's what the intent of this problem number 4. So this data structure in the linear list data structure applications, majority focus is on how do you practical requirements map to linear list. When the list makes sensible, when linear list, when circular list now. Here linear list is more than enough here. Here we circular list makes sensible. You need to have comfort with both of these data structures. That's what the problem number, 4, broken keyboard problem. So the link is given also here. You can go to the link, that's where the problem was taken. So that's all about that assignment. Now, so if you have any questions basically here, I'll take up, whatever you have it up. So otherwise, we'll take, we'll go to the next, we'll discuss next session now. Any questions you have it up, let me see. Live, I don't see any questions now here. So next session, all you got to do here is go to linked list now. Solve those problems here. If already done, no problem. I'll take up next session for discussion of, linked list problems now. So until that, so that's all now. So that's all end of this, what do you call, session.